have a quorum here, so I just started the live broadcast of our Hangout. And since it's 8 o'clock here, our time, I think we'll just go ahead and get started. So this will be, we wanted to do these, I think part of the idea was to have more opportunity for discussion, question and answer dialogue on some of the work the basement is doing. And so I'll probably take maybe 25 minutes or so to give an overview of some of what Lynn is pushing us to look at around the water crisis and the drought situation. So just to go into it, I mean, I thought what Lynn had to say today in the NEC was very good. The point is, in dealing with any of these crises, we're not talking about just some fixed, static solution for any particular thing. We're not looking for some fixed, specific program per se, as a program as such that we need. We need the, as Lynn said earlier today, he said we need to change not what people think, but how they think. We need to change the way how people think, what people think about what mankind is. And the point is, mankind is a willfully creative species who is creative specifically by the means of his own willful creative action to constantly go to higher states. And I think this water situation itself is a very good example of that. Is if you look at, I pull up the first graphic here, you look at the early, a century ago, less than a century ago, you look at the type of projects that were done in the Tennessee Valley to address the water crisis in the south region there. You had a situation where to deal with the river flooding situation, the water needs, the power needs, we had at the time, massive, huge revolutionary project to tame a section of a single river basin. And at the time it was a huge, massive project and a revolutionary demonstration of what the human species can do to improve and control his environment. You saw the continuation of those policies. If you go to the next graphic here, you have another very good case study of taking this concept a little bit further. Or if you look at the water programs of the West, of California, of the Colorado Aqueduct Project, of the California Aqueduct Project, where now you had extending this idea of water management, water control, river diversion systems further. You had a larger scale project completed over in a couple successive stages back in Roosevelt's era, and then with Governor Pat Brown's projects following that, you had the management of the California seaboard river basin systems and the interbasin transfer from the Colorado basin over to the California region, as you can see here. So this was a natural evolutionary step to a larger degree of control of a larger water system to correspond with the growth and development of mankind following the activity of the TVA. So then in this context, by the 1950s and 60s, you started to have discussion and study of the NWAPA project. And this is a completely natural extension of where mankind was going in improving his ability to control and develop large territories. And this brought us to thinking about not just a section of one river basin, just one river valley project, not even just an entire, not even just an integration between a couple river basins, but people looked at the more or less the entire continental water system and a number of major basins involved, and designed the Nawapa system to think about mankind managing and developing nearly a continental scale. As you can see on the map, this touches pretty much everything except for the south, but it does have direct impacts on the south as well. So it's really a continental scale, especially with the extensions that we were looking at, a continental scale water management system. So this already by the 1960s was realized as the natural progressive next step for mankind to improve larger and larger water systems, to have more stable and better control over water flows for agriculture, for human water needs, for everything you need for society. And really, this is a very good example of people have been participating in Jason's So You Wish to Learn All About Economics class series. You know, this is a good, very critical example of increasing the potential relative population density. And this is mankind really transforming the relative factor of the relativeness of a territory that the human economy is employing. But then, as we know, so this was designed, planned in the 60s, and as we know, this Nawapa project was not built. It would be a completely different situation if it was. Much of the crises we're facing now would be much easier to handle. We'd be in a much more stable situation, but this was not built. And I think everybody on this broadcast knows why this was not built. You had the introduction and then dominance of this entire green genocide paradigm, this zero growth, zero progress paradigm coming in, a major shift with the assassination of Kennedy. And then by the late 1960s, a solid shift away from the idea that mankind should have any progressive influence in the environment, and this idea that mankind's activity is somehow inherently bad or inherently problematic on the planet, this anti-human conception that was introduced. And the Nawapa is a case in point, perfect case study expression of this. You know, Michael Kierce led up the production of the Nawapa feature film, where, what was the title? Is there?
Nawapa 1964.
Oh yeah, Nawapa 1964. And in that, it's a very good, if people remember it, if they haven't seen it, to go back and watch it. You can see in the letters between the senators, between Frank Moss, between the supporters of Nawapa, the people campaigning for Nawapa in the 60s, you see in these personal correspondences a very clear and substantial reflection of the cultural shift that occurred, where the optimism of transforming the entire West with this great project was completely overturned, and you just started having this creeping green pessimism, cynicism coming in and dominating the way people were thinking about these types of projects and about mankind as a whole. So that has been now 40 years of a no progress policy, typified by the fact that we don't have Nawapa, typified by the fact that nuclear power has been frozen and halted, typified by the fact that fusion has been suppressed. But as again, I'd like to directly reference what Jason's doing with the So You Wish series, because this is, I think, a good reference point for some of these concepts. This has not been just simply a pause in mankind's progress. Stopping progress doesn't mean you just hold at some state. It means you actually begin a process of collapse, of decline. By not moving to a higher state, by not moving to a greater form of control and management and improvement of the territory, and by staying fixed at a certain state of the economic development of the U.S. economy, we've introduced and now suffered 40 years of an attrition factor, which has greatly accelerated the crisis that we're now facing today. On the one side, I'll say just briefly, this idea of this concept, I think, is a critical thing for people to really work with, and it's very important for the organizing, because people have to be broken from this idea of some steady state universe. They're always thinking about some stage we have to get to. We got to get to this stage or that stage. We need this thing or that thing. But it's a completely fallacious view. What's real is processes of development. And this is true about mankind, but this is true about the whole universe. This is true about evolution. The evolution of life has never been governed by reaching some state, but it's always a process, and the process is always characterized by a directionality to a new stage, a new level of development. So what's real is not any given state in and of itself. What's real is a process of going from a lower state of organization, a lower state of energy flux density, even in the biosphere, a lower state of biospheric energy flux density, to then going to a higher state, a higher level. And it's that process of change which is really the substance of the universe. And I would even argue it goes outside of the Earth system. If you look at the development of solar systems or galaxies, I think ultimately that is what you're going to see, is the fundamental characteristic of the universe that we can ascertain and discover. So it's the same for human society. These past 40 years of a zero growth policy have created and built up a major crisis, and you can see it just by the attrition factor. If we go back to the graphics, I mean, there's a lot of ways you could look at this, but just to give a few, one simplistic, very clear, straightforward example, if you look at the aquifer situations across the United States, because we haven't built NWAPA, we haven't built a continental water management system. So many territories of the United States, many farming territories, have been relying on depleting a finite groundwater supply. And in many places, in most places where these things recharge, the rate at which they're being recharged is much lower than the rate at which we're withdrawing the water. So this is a very clear example of the attrition factor that we've built up by not going with NWAPA, by not going with these large continental water projects. So this is something that we now have to overcome, something which wasn't the case necessarily. There might have been some aspects of this, but it wasn't nearly as bad in the 50s and 60s when people were designing and thinking about the NWAPA system. There's another factor that makes the situation today different than what was faced when NWAPA was built, and that's just when NWAPA was being designed, and that's just the immediacy of the crisis. As we've discussed, the California crisis is existential and right now immediate. We've already lost over 500,000 acres, over 500,000 acres. It might be higher at this point. I haven't been watching in the very recent period to see if it's increased, of some of the most highly productive farmland in the entire country is going unplanted. It's not going to be developed. Another year of this drought, you could have the same or more loss. Another year after that, you could have the same or more loss. So we don't exactly have decades to act to build a continental scale system. That won't address the crisis that's right here today now, and it is outside of just California. Texas also has similar conditions, but these are major food suppliers for the entire country. So this is not limited to any one region. So you have a second factor. You have the attrition factor, and you have the factor that the immediacy of the drought situation has gotten much worse. So both of those make the situation very different today than the situation was when NWAPA was first discussed and designed. But I want to take some time now to focus on a third factor that makes the situation today and how we have to think about the crisis right now very different than what it was 50, 60 years ago. And between these three factors being the reason why Mr. LaRouche is pushing us to reconceptualize and rework the water crisis and the situation from a fundamentally higher level at this point. And that third factor is the role of actual real changes in the climate, real climate change. Not the lie, not the claim that driving your car is going to cause the Great Lakes to evaporate or something, but the fact that the climate system of Earth is very dynamic. It's very complex. It goes through large fluctuations, and quite frankly, some of these fluctuations occur on much shorter time scales than many people tend to believe or think. And then we'll get into some of the key factors in this are solar activity and galactic activity. But just to look at the changes, this is a study that we've referenced a number of times that I think is important, which is just looking at the situation in the West and in California. This here is an image of a tree that is probably somewhere a few thousand years old. These are called Bristol cone pines, and they're found in California, they're found in the West, and they can live actually up to 5,000 years old. They actually have some that are over 5,000 years old that are still living. So these things actually, by examining the tree rings and the isotope fractionation in the tree rings, these things actually keep a very clear record of the climatic conditions over thousands of years in the West, including moisture and rainfall and how wet it was in certain regions. And by analyzing these thousands of year old trees, we see that in the West and in California, the past 2,000 years has been a very dynamic and fluctuating period with repeated prolonged periods of what they call mega drought. And I guess you'd call it mega drought relative to what we've experienced over the recent period. And then even punctuated by periods of what they call mega floods, where the entire Central Valley of California has been flooded many feet deep, tens of feet deep throughout the entire region through major atmospheric river events and different things dumping huge amounts of water into the California system. So what we know about the climate of the West and of California is that on average, well, overall it's fluctuated much more than we've experienced in the recent period. On average, it averages, frankly, a lot drier than what we've experienced over the recent period. And it has relatively regular mega drought periods. And relative to these conditions that we actually now have records of showing us that these are the conditions that California and the West has experienced for the past couple thousand years, the past century relative to that, the past 100 years, 150 years, has been somewhat of an anomaly. It's actually been much more stable than would be expected by the record prior to that. It's actually been wetter, moister than was expected prior to that. And this is very important because the entire California water system was built and designed from the standpoint of the water conditions that were experienced over the past 100 years, which we now know are not the regular conditions that we can expect in this region. This is important because Nawapa was designed from the standpoint of what we experienced in the West in the 50s and 60s, which is not what this region, which is not what we can expect to continue in this region. So some of the people doing these studies, they're not necessarily making a forecast as to what we're going to see next year, but they're saying it's certainly possible that we're not necessarily entering a drought period, we could actually be more of returning to the types of regular conditions that the region has experienced. So that is an example of the types, and these changes can come on decadal scales. These are not just like over 500 years, a very gradual, slight change. You can have over the course of years or decades or less than decades, you can have the onset of these periods of mega drought, and they can last for decades or century or longer. You can have within a year or a couple of years the onset of periods of mega flooding. So these are not very long-term gradual things. So these are the types of changes, dynamic fluctuations and changes that we know have happened. Now, in this California in the West, as an example, is a case study. Now, why did it happen? There's a lot of factors. What I want to talk about is the role of solar activity in particular. The role of solar activity in the situations in California and the West, which I was just discussing, I haven't seen any specific studies looking at the role the sun played in the changes in the West specifically. So that's an open question there. We do know that changes in ocean activity play a major role. There's periodic fluctuations in ocean currents and ocean temperatures which play a major role. That is a factor in California and the West. But we're digging through literature right now. We're kind of trying to do an overview in the basement, getting a better sense of what are the array of different records and correlations and evidence indicating the role of solar activity on climate and weather changes on Earth. So the California one we don't necessarily have anything specific on yet, but I wanted to give an overview of a few other cases where we do have pretty clear evidence of solar activity playing a major determining role in these changes. So this is a, we're going to kind of jump around on a number of time scales here, but I kind of wanted to just give people a broad sense of the types of things that's going on that we have to take into account. This is a study looking at the past 12,000 years. So I was just talking about the previous 2,000-year period. Now we're looking at the past 10,000-year period, or 12,000 years. And what we see here is two different measurements of cosmic radiation activity, galactic cosmic radiation activity. Both of them measured against ice flows in the Atlantic Ocean. So the black curve is a measure of what they call ice-rafted debris. And just like that sounds like, that's debris, it's material that was brought, it was moved by ice flows, by large flows of ice. And so they can look through the settlement of this debris and get a record of how much debris was moved by movements, large movements of ice, and they can then get a sense of that it obviously must have been a lot colder if you had more ice and glaciation activity going on. And what you see in these examples is that the increase of ice flows corresponds very tightly with fluctuations in galactic cosmic radiation. And galactic cosmic radiation, so when there's more galactic cosmic radiation intersecting the Earth's atmospheric system, at least we know here in the Atlantic region, it tends to get a lot colder. And one thing we know of that can modulate and affect how much galactic cosmic radiation is coming at the Earth is the sun, is the role of solar activity. When the sun is more active, when the sun is vigorous, magnetically active, doing a lot, it's got a lot of sunspots, it's sending off coronal mass ejections, it's shooting off solar flares. When the sun is really hyped up and active, the whole magnetic field gets a lot stronger, and it tends to block more galactic cosmic radiation from coming into the inner solar system. When the sun takes a breather and cools off and slows down and takes a rest, the solar magnetic field, the interplanetary magnetic field, gets weaker, and more galactic cosmic radiation comes in, which we can see measured by these lines here, the red and the blue. And as we can see, that corresponds to this cooling, this increased ice flow in the Atlantic region. So we know this is one example. We know that very closely tied over the scale of thousands of years, 12,000 years, not even a huge time scale, the cooling effects corresponds with solar and galactic activity. Go to the next graphic here. Again, we're kind of bouncing around just to give a broad sense of some of the things we're dealing with. This is a graphic looking at India and looking at the monsoon, the strength of the monsoons, the huge rainfalls in India from a period of about 6,500 years ago to 9,500 years ago. And I actually forgot why they picked this slice of time in particular. I think they might have had better proxy records, better data from this particular time period for some reason. But in looking at this 3,000-year period, they saw that, again, there's a very tight correlation between galactic cosmic radiation, and which is intimately connected, again, to solar activity. So there's a tight correlation between galactic and solar activity and the rainfall, the intensity of the monsoons in India. And what they found is that when solar activity is low, when there's low solar activity, and meaning there's higher galactic cosmic radiation, they find that the rainfall decreases for this region of India in particular. That doesn't mean that'll happen everywhere the same way on the globe, because the whole climate system is very complex. Ocean patterns, wind patterns, a number of factors playing a role. But this record here at least shows us for India and for the monsoons in India, it's the case that when you have lower solar activity, you appear to have less rainfall. So that's an interesting case. Go to the next graphic here. Jumping to a bit of a shorter time scale, something that's a little bit easier to grasp. This is about the past 1,000 years. And this is just a measure of solar activity. And people might be familiar with the name on the right about 300 years ago, the Maunder minimum, which has been referenced as a very interesting period in both solar and Earth climate activity, where you had no sunspots for some decades. And so again, this was 300 years ago plus. But even back then, even back that early, people were actually looking at the sun, not in the middle of the day, but looking at it during sunrise or sunset with the naked eye. Don't recommend you do that necessarily. We have much better. You can go to NASA's website. We have much better cameras that look at the sun for you. You get better pictures too. But they had already been observing sunspots, these little dots on the sun. And prior to the Maunder minimum, they were regularly recording sunspot activity on the sun. And they had records of sunspot activity on the sun. And remember, sunspots kind of are a good indication of overall general activity, magnetic activity, etc. It's a good sign that the sun is active. But then all of a sudden they disappeared. And there was a period of a couple decades with very low solar activity, and even some period where there was literally no sunspots at all. And this corresponded to very likely cooling across the entire planet. It's most well documented in Europe, where you had what's called the mini ice age. You had a major ice age, you had a major cooling event throughout Europe, which actually corresponded to famines in certain cases, actually had significant impact on the crop, on the food production of certain regions. Regions that were kind of just borderline for certain crops, where normally year to year you could get away with growing certain things, all of a sudden the temperature dropped just enough that they couldn't grow things anymore. So this had major effects even on the economy at the time. And this is well recorded in history because it was relatively recently. And it's somewhat a subject of debate, but there's I'm not up on all the details of where it's at immediately today, but there's some evidence that it was indeed global cooling. It wasn't just cooling in a few regions. But as you can see, the Maunder minimum was just one of a whole series of major solar minimums, what are referred to as grand minimums, where the sun gets very weak over successive solar cycles. A solar cycle is about 11 years on average, give or take. It varies a little bit, but every 11 years or so, the sun goes through a period of low activity to high activity, back to low activity again. That's a full 11-year cycle. But if you add up those cycles over centuries, you notice that overall the cycles will tend to each be stronger for a period, and then the cycles will all tend to be weaker for a period. And when you get a period of weak cycles or even no cycles, these are these grand minima. And this is what we see indicated here on this graph over the past 11,000 years. You have the Maunder, the Spoor, Wolf, and the Oort minimum, a series of grand minimums. Now if we go to the next graphic, it's a little bit messy and ugly here, but this is a measurement from China, looking again the past 1,000-year period. Here on the black thick lines on the bottom, the little dash, the big thick dashes, the one on the starts with DM, that refers to the Dalton minimum. The next one's the Maunder minimum. Was the one before that the Spoor minimum, or Sporer minimum, and the Wolf minimum and the Oort minimum. So again, these are these grand minimums, but what the graph indicates is precipitation in the Tibet region of China. So here we have another indication of low solar activity corresponding to drought conditions in a certain region of the world. So in this case, this is a relatively recent study by some people out of the Chinese Academy of Sciences. I think it came out this past year or so. And so they showed that, among other things, it was a rather lengthy paper, but among other things they show that the drought conditions specifically in the Tibet region of China correspond to low solar activity, these grand solar minimums. And again, it's not totally clear if it's going to be the same everywhere on the planet. It's not necessarily as simple as low solar activity means drought globally. That might be the case. It might not be the case. We haven't seen any studies yet that indicate one way or the other that simple of a statement. What we've already seen is a clear indication that there's different regions of the planet are subject to different influences from the climate system, and different regions certainly have shown evidence to responding very strongly to this type of solar activity. I'm going to look at one other study just to give one last sense here on the solar activity. This is actually one I think Cody Jones just dug up the last couple of days. I just had a chance to skim through it. But this is looking at a much shorter time scale. This is just the past 100 years. So the previous ones were looking at thousands of years. This is looking at past 100 years. Again, in China specifically. Now this just deals with we haven't had any of these grand minimums. So this doesn't deal with any huge variation in solar activity. But this is just the general cycle-to-cycle solar activity over the past 100 years. And what they did was they looked at the rainfall and the monsoons throughout China. And they said, are there any regions of China where the intensity of the monsoons and the rainfall correspond strongly to sunspot activity, where if you have more sunspots, you have greater rainfall? And they found that it wasn't necessarily the case that the whole country responded the same way. But they did find a couple of these regions in central China, as you can see. The black, and the dark regions are regions where you have a very strong correspondence between sunspot activity and rainfall, where more sunspots would consistently over 100 years correspond to more rainfall, and fewer sunspots would correspond to less rainfall. So that's to kind of just give an overview of, again, we're digging through a lot of papers and studies, and there's a lot else out there, but I want to kind of just give a sense that there's some very strong patterns indicating that the climate system is very intimately tied to what the sun is doing. Now, what is the sun doing now? This is the past 250 years or so of solar cycles, and I believe these are probably counted in sunspot number during each cycle, and you can see some cycles peak much higher than other cycles. We are right now in the middle of solar cycle 24 on the far right. We're basically just at the peak. And I believe this graphic was probably made a couple of years ago, because the peak is actually less than what they have it drawn on here. But this was all over the news of the past few months. It became clear that this current solar cycle we're in the middle of has been the weakest solar cycle in over a century. That the number of sunspots, and now we can actually measure a lot more, the strength of the magnetic field of the sun, the magnetic activity, the amount of geomagnetic storms created on the Earth by solar activity. All these things are declining. They're getting less. So this past solar cycle has been as the weakest in over 100 years. And at this point, there's a number of projections and forecasts that the next cycle could be even weaker. And so it already looks like we're heading into a Dalton minimum type event, where we could be seeing a couple of successive solar cycles, which are relatively weak solar cycles. It could be an even weaker, we just don't know, it could be a weaker period. It could be more like the Maunder minimum, where you had no sunspots. You had basically no solar cycles that you could tell about for some decades. We're not totally sure. What we do know is that the sun seems to be heading into a period of low solar activity that we've actually never experienced in the modern age. Here's another graphic. I just pulled this up today. This is dated as of April 7th. So as of a month ago, this is the number of sunspots in solar cycle 24, and you can see we're kind of just heading up at the peak there. And the red is the projected decline of the cycle we're about to go into. So the point is, we know that the sun does have a very significant effect on climate conditions, on moisture patterns, on temperatures in different regions of the planet. We don't yet have a fully clear idea that would allow us to forecast exactly what's going to happen and where. We do know that this is something we haven't experienced in the modern age, and so we can't assume to know what the effects are going to be, other than we should be ready for and be prepared for significant changes to the type of system that we'd experienced over the past 100 years or so, which is, again, consistent with these studies from California and the West that I was referencing earlier. So these are the things that we've been looking at for the past couple months, frankly, off and on. And at a certain point recently, Mr. LaRouche basically just said, look, we got to quit kidding around and actually look at how do we overcome and deal with these active factors in the context of the drought and the global water crisis. And this does not mean how do we look at these different things individually from the standpoint of how we were thinking before, but how do we think about all of these factors coming together? The attrition factor in the physical economy, the immediacy of the crisis in California and Texas and the West, and the major fluctuations and changes we can expect from changing solar activity. If you take all these new factors that weren't the case when that weren't conscious or known or the case when NWAPA was originally designed, and they weren't clear to us even a couple decades ago when we were re-pushing NWAPA in the 80s. How do we think about all these factors and come to a higher order conception of what mankind must do to handle this current crisis, this current drought, this current water crisis? And Lynn was very hard and firm, saying we can't just stick with plans and ideas that we had years ago just because we're comfortable with them. Our ideas and the level of intervention and development and control that mankind needs to exude over the biosphere and the planetary system has to evolve with the development of society, and it has to evolve with these changing solar and galactic conditions. We have to be thinking about pushing what these new factors I just outlined. They force us to think about how do we come at this from a higher level. How do we think about a new subsuming concept that will allow mankind to handle these crises and deal with these crises and deal with these types of changes? Now, there's two ways you could look at that. We've done a lot of work on the first way already, which is basically just increasing the quantity of control. We took NWAPA, we reworked NWAPA as NWAPA 21. We reworked NWAPA with nuclear power to allow pumping of more water through the system. We looked at integrating NWAPA with additional extensions, stuff we discussed in the past, stuff Dennis Small and others have looked at with integrating NWAPA with southern systems that could bring water from southern Mexico north, kind of linking both two areas of high water concentration in the continent to fill in the rest of the continent as a full-scale continental project. We looked at additional extensions which can bring more water to different regions. So we pretty much did an exhaustive study of quantitatively how can we increase the control and redistribution of water, the river patterns, the river systems of the current North American system. But at this point, what we really need to look at, what these considerations force us to do, recognizing the immediacy of the crisis, the depth of attrition built into the physical economy currently, and the fact that we're ready to see changes that we have not experienced yet in the global climate and weather systems. That we have to think not just about quantitatively increasing the system, but how do we qualitatively come to a higher level of NWAPA and water management globally. And so what we've started to look at is quite literally going to a higher dimension. Quite literally going from a two-dimensional system where you're dealing with the surface of the earth, you're dealing with the existing terrain, and you're saying, where is water flowing already, and how do we get it to where we need it? A two-dimensional view of water redistribution in the water project. We need to go to a three-dimensional view, a higher dimension concept of what determines where the water is such that we could redirect it or utilize it. Why is there water in the north? Why is there water in the south? What factors ensure that water's where it is? How might those factors change when solar activity changes, and how would that affect our water redistribution projects? So, I mean, quite frankly, this is something that Mr. LaRouche has kind of been pushing for a longer period, off and on, to look at the global atmospheric moisture systems which subsume NWAPA and subsume other water projects around the world. Couple more graphics here to indicate some of this. So here's a somewhat pixelated, not the prettiest graphic, but here's a graphic based on NASA data of global rivers, river flows around the world, and the darkness of the blue corresponds to the amount of river runoff, water flow in different regions. You can kind of just intuitively see quickly where the water is and where you have a higher rate of water flow. This is not, all this evidence of the solar activity and correlations of changes in solar activity to climate conditions, as that indicates to us, this is not a permanent fixed system. This is what we experience currently, but we have to be thinking about thinking about how these systems are going to change and what determines the precipitation patterns, where the rain falls from the atmosphere, such that you have this or any number of different changing systems of river flows and water flows. And so what we're looking at, it's kind of the last graphic here. Hopefully this doesn't get too confusing, but this is a schematic of the water flow, the average annual water flows of the global water system as we currently understand it. This might take a little bit of time for people to get fully familiar with, but you have, obviously, the biggest store of water on the entire planet is the oceans, the ocean system. And you can see on the far left, you have a figure, an arrow pointing up from the oceans up to atmospheric moisture. And the number next to that figure is 413,000. Now that's 413,000 cubic kilometers of water flowing up from the ocean to the atmosphere every single year. And I went through some of these figures. I can't necessarily remember them all off the top of my head, but I think that was something like 20,000 Colorado rivers flowing straight up from the ocean into the atmosphere. So it's a huge, huge volume of water every year flowing up into the atmospheric system. For scale, for comparison, NWAPA, the full NWAPA 21 plus program with all the extensions, might get up to around, I believe, 200 cubic kilometers a year of moving of water in North America. So that's 200 cubic kilometers compared to the oceans constantly pumping up every single year, almost 500,000 cubic kilometers. Now, as you can see, 373,000 of that then falls back down onto the oceans. That leaves 40,000 which didn't fall over the oceans, meaning it fell over the continental land area. You can see that on the very top there, that 40,000 leaving the atmospheric moisture and moving over to the continental land area. But the total amount that falls as precipitation over the continents, over the land area, is 113,000, which includes, as you can see, 73,000, which comes from the land area itself. So more of the rainfall that falls on land is water that actually was already on land, that evaporated and then fell as water again. And there's some other interesting factors where you can look at the division between how much of the water that comes from land comes from plant life versus from regular evaporation. But this, getting into some of the details on it. But the point is, there is more than enough water in the atmospheric system than we need. this 413,000 cubic kilometers a year is a huge, huge, massive continuous flux of water into the atmospheric system. And this is what determines the feasibility of, this is what determines all of our river systems. This is what gives us our snowpack, that gives us our melt in our rivers. This is what makes the TVA possible. This is what would make NWAPA possible. This is the higher order source of all the land area, all the two-dimensional water flows that occur all over the surface of continents around the planet. So if we're going to deal with both with the three aspects that I went through in the beginning, the immediacy of the crisis, the immediate threat to the food supplies, the 40 years of physical attrition into our water systems of our physical economy, and the higher degrees of fluctuation and change of the global and regional and sub-regional climate systems with the coming changes in solar activity, we have to go to this higher order conception of the systems that subsume any and all river diversion, water diversion systems, and start to look at how we can begin to affect the climate and affect the precipitation patterns and modulate rainfall, where it falls, when it falls, how much falls in different regions, how we can ensure rain doesn't fall in regions where we don't want it to fall. And this is something that we've been challenged to take up, but there's already existing studies that even on, at least on a small scale, some of this is already being done, and much more could be done just with relatively smaller scale systems. Now you have cloud seeding. That's something that's been known for a long time. But you also have an entire area of study looking at modulating the electrical and ionization activity of the atmosphere, which can give us a direct handle and control on rainfall patterns and potentially moisture flow patterns. And I actually wrote an article on this last year called, I believe, Expanding NWAPA 21. I forget the title now.
Weather modification
to
prevent starvation.
Weather modification to stop starvation. And that gives a case study of at least 3 nations where they've been working with these types of systems and have clearly demonstrated that you can have some effect on precipitation patterns and rainfall patterns by modulating these electrical properties of the atmosphere and these ionization conditions of the atmosphere. But that's kind of just a very beginning touch, scratching the surface of what we could potentially be looking at and doing if we decide to take up this as a serious mission, as a mission that our food supply, our water supply depends upon as a nation and as a collection of nations. So that's something we've been looking at, and I'm here and a few other basement members are here, and we'll be happy to take questions and comments, have some discussion on what we've gone through and where we need to go with some of this work.
Can you take questions?
Sure. No.
Well, I want to know if we know the relationship between the atmospheric water and precipitation. Is it always in equilibrium? Because it would seem like there might be factors that would make the atmosphere retain a lot more and not precipitate. And is there any, or vice versa? So do we know what causes that or how it works?
Diane's here in the live studio audience, and yes, they're alive. Yeah. she asked how much we know about what factors determine how much moisture the atmosphere can hold, why it holds a certain amount, does that change? And I'm actually not too sure. It's a good question. That's a very good question. I'm not sure if the the numbers I gave in this chart are just averages. So that I'm sure that fluctuates. How much it fluctuates, what conditions. I mean, I'm sure temperature plays a role. I'm sure these ionization systems look at the electrical properties playing a role, and also the amount of ionization in the atmosphere. When you have more ionization, it helps clouds form and water droplets form. So if you have less, it might be lower the potential for the whole storage. That's a good question. I'm sure there's a number of factors, but we don't have a full overview of that.
Since I'm sitting right next to her, can I ask a question?
Sure.
How do we know that the amount of water that's in these atmospheric rivers is going to be constant? Why would it not be affected in the same way from solar activity and whatnot?
So Alexandra is asking, how do we know that the atmospheric rivers won't also be affected by changes in solar activity? How do we know that they're going to continue to be a source, basically? Yeah, it's another. I mean, the atmospheric rivers are very dynamic. They actually change a lot. They're actually only there, I think, for a few days. So it's not like a river on land where it's constantly flowing. It'd be nice to play some videos. I don't have anything set up where I could show it, but NASA and NOAA, they've done some animations and videos showing how these things actually change and fluctuate. So they're actually pretty dynamic structures. They're not fixed in the same way the Amazon River is just flowing from its origin to the delta. But as far as we understand, the biggest factor in the evaporation of water, as far as I understand, I think it's just the basic total solar radiation output. The amount of light electromagnetic radiation that the sun gives off. As far as we've seen, that doesn't actually change a whole lot between solar cycles. That actually stays relatively constant. What seems to change a lot more is the magnetic activity, the solar flares, the coronal mass ejections, and then also some of the more extreme forms of electromagnetic radiation, like higher ultraviolet, more intense ranges of ultraviolet. That can change a fair amount, and then also X-rays will change a lot. So it's a very interesting thing to look at. It seems that the main source of evaporating water and bringing it up into the atmosphere, the main forms of sunlight coming out, stays relatively constant. So I don't think we've seen anything to indicate that there might be any huge drop in the moisture availability in the atmosphere. But that's a good question to ask and look into and think about.
Well, changed. I mean, think about Sensmark's experiments. I mean, the cloud cover is being changed by the sun's changes in this way. That'll affect how much evaporation occurs.
Right.
People also might not know that you muted them. Remind them.
Jason also brought up the fact that there's evidence that galactic cosmic radiation can play a role in creating more cloud cover, and that would then block more sunlight from coming down to the oceans and evaporating water from the oceans. So that might be a way that these changes in solar activity or potentially changes in galactic activity could affect the flow of moisture into the atmospheric system as a whole. So we'd have to figure out how to keep those clouds away if that's becoming a problem.
Just keep them over land.
Keep
them. Hi, Ben. It's Mindy. I had a question, which is, how do we create the ability to get the water in these rivers down here?
That's a good question. That's that's exactly what we're trying to look at and take up that challenge. I mean, there's a few things. One, there might not be ways that we yet know that we have to figure out. And I have no doubt that if the United States was actually operating under a top-down science driver program, we actually had the mission and objective to do this, and especially in cooperation with nations like Russia, China, and other places, I think there's no doubt that mankind could begin to figure out ways of modulating and affecting these systems in a very efficient way. We do know that there's studies on these ionization systems which have shown to be successful. Mexico had a whole series of these stations operating across the entire country for well over a decade. Australia has a company called Australian Rain Technology, and they have a very open website with open studies and literature showing that they've done 3 case studies now, which very clearly show that there's some positive effect of the systems that they're using. The United Arab Emirates had a operation going there, which hit international news a couple years ago, and there's indications that this has been done in Russia and other places. But this particular technique is basically dealing with ionizing the atmosphere. So normally any atom has the same number of protons and electrons orbiting around it. So it's neutral, it doesn't have a charge. Most of the air in the atmosphere doesn't have a charge. You can use an electrical current to partially ionize sections of the atmosphere, which would separate a few of the electrons from the atoms, and you'd create ionized particles, ions, which is an atom which doesn't have an equal number of electrons and protons, so the charge isn't balanced out. It has an overall charge, positive or negative. We could use, these systems use electrical currents run through wires, large antennas. You run the right type of current through these wires, and you can ionize the atmosphere around the wires. And these ionized particles, with their charge, actually become the seeds for moisture droplets, for clouds to form, for moisture droplets, and eventually help to generate rainfall. So you can actually, by increasing the ionization, you can induce more cloud formation and induce more of the water vapor to condense around these ionized particles and form large enough masses of condensed water to then fall out as rain. So that's what these systems are operating on in terms of what they are designed to do. And I believe in Mexico they even had one of these stations. I'm actually not familiar with exactly how they get it to work this other way, but they even had one of these stations set up to inhibit rainfall, to inhibit cloud formation, to actually stop rain from occurring in certain regions where they didn't want it to occur. But that's the one documented method of inducing moisture in the atmosphere to condense, move from a vapor state to a liquid state around these ionized particles, and then form large enough droplets such that it'll fall under its own gravity down to the ground. Now, there's a certain idea that potentially if you have enough of these stations covering a large enough area, you can even potentially create drafts of moisture, potentially bringing this moisture from over the ocean further inland by operating enough of these stations on a large enough scale. So that's something that they were looking at in Mexico with the Mexico systems, where they had, I think, 28 of these things operating.
Pat, I think you can speak if you want. Pat?
What?
You want to say something? Try it.
Microphone is crossed through.
Try it anyway.
Ben, you hear me?
Speak up.
Yep, I can hear you.
Okay. This is Pat Rucker. I've got a couple comments, then the question. When you were discussing the California water project of Governor Pat Brown, it's also important to point out, I think, that those engineers and the designers of that project in the early 1960s, said repeatedly that when we complete this a decade from now, we have to immediately begin the next even bigger project, and that was NWAPA. They were not looking at that project as being the end of it by any means. And that was characteristic of the Kennedy era of looking, always ahead 10, 20, 30, 40, 50 years. That's one point. Secondly, your point on attrition, which I found quite provocative, in that since we did not build NWAPA, the continued reliance on groundwater, pumping water out of the ground through wells, has increasingly, especially in this drought, really taken a dramatic leap upward. And the study that came out a couple days ago shows that thousands of wells in California have already been or need to immediately be deepened by as much as 100 feet. So we've got a collapsing water table now, and on top of that, then, as the water table collapses, then the ground collapses, and you get subsidence of the ground level, and as much as in some areas of California now, a foot per year. Right? So that was the second point. Third point was the, no, I guess that was 2 points I wanted to make. Now, the question, I mean, what we're looking at now, what you've so thoroughly gone through in terms of a strategic scientific thinking on, what creates the existing water flow pattern or precipitation pattern or atmospheric water pattern, is obviously something that's over the next decade or two before we really start getting a handle on it, as would be NWAPA, if that was built as currently designed, right? But I don't think we've been putting enough emphasis on the desalination, nuclear desalination, and I think that is an area that we really, I think, should be hitting much more vigorously on. So that was the point I wanted to raise in your comments on that.
Yeah, absolutely. So useful to have those examples of the wells in California. That's good to know the specifics on that. This point on the designers looking of the California projects looking to NWAPA, I think that's exactly, that's a type of, that's the type of process that we saw cut off so clearly. Like I was going through with the example of the NWAPA 1964 video, it was so clear when you saw a shift in the fundamental way people were thinking across the whole country. That it's not think it's a very good example of it's not about a project. It's about a conception of what mankind is. It's about a conception of what do we want to do with society? Where do we want to go? What do we want? What conditions do we want to create? How can we improve things this next year, this next generation? So I think it's a very good example you're bringing up, that, it's not like the California water project. People were just like, this is it, this is the project. They're thinking about this is part of a process of mankind, of our nation, coming to improve the territory as a continual process. And I think is a very good example of that. And on the desal, absolutely. I mean, what we need is a top-down mission to save the nation. And if we had a Kennedy or a Franklin Roosevelt, if we can get a president who's a patriot and not an agent of the British Empire, like the last two presidents we've had have been, there's a number of immediate things that can be done. I mean, if we need to bring in water in trucks to keep a few farms alive, we will do that. We will do whatever we need to do to keep our food supply, to keep our farmers alive and active and working. I mean, they're already trucking around water for fracking. They can do that for fracking. We can sure as hell do it to keep our farmers alive. We can sure as hell look at desalination as a medium to shorter term measure that can be taken to begin to alleviate these emergency conditions in certain coastal regions, which will then have cascading effects further inland, by meaning that the cities won't have to draw as much water from inland. So if the cities are getting their water from desalination, it will allow more water for the farms and counties and other regions further inland, because they wouldn't have to give their water to the coastal cities as much. But I think what we need to look at is just how do we organize all of these options from the standpoint of a single conception. And the single conception that mankind is being challenged with by the conditions mankind is facing is how do we think about, conceptualize, and act on the global water system as a whole, including the whole atmospheric system. And how do we not just throw that out as a phrase and then go back to thinking what we were thinking before, but how do we actually develop that as a actual higher order concept from which any and all of the other options, shorter term options and longer term options, are subsumed and flow from that as the goal that mankind has to be thinking about. And I believe someone else sent in another question on, it was Dash, on what role fusion can play in aiding this process. And I mean, there's things we need to look at more closely, but most immediately, fusion desalination is a serious option. Leona picked up a preliminary study by a scientist over at Livermore who was looking at fusion desalination to support 13 billion people on the planet. So there's some good studies of people thinking on the right scale of activity. I don't know if we need to just go straight desal for the whole thing. I think if we look at these larger atmospheric systems, we could potentially find some subsuming ways to handle the larger process as a whole. But as part of that whole package, fusion desal is certainly going to be a critical component, as part of a whole fusion economy over the next 1 to 2 generations. The other thing to think about is just Lynn's conception of national energy flux density. What's your energy flux density in terms of power per capita and power per square kilometer? What's your energy flow per person and your energy flow per square kilometer per area of your nation? Fusion will allow us to move to a much higher energy flux density national economy. we could have a higher power per capita, higher power per square kilometer. And with a higher degree of energy power allotted per person, that frees up more, that gives you more physical ability to do more to support each person on average. So it'll increase the physical energy, physical free energy of our national economy as a whole, to the degree we can begin to afford, physically afford, in physical terms, higher energy input into securing, ensuring, purifying, transporting, and taking care of our water system as a whole. So just from the standpoint of the top-down national territory as a whole, a fusion economy will allow us to do much more on these, in all these areas, because of the higher energy flux density of the economy as a totality.
Hi, we got a question here.
Yeah, can you hear me?
Yep.
All right, two questions. I was curious to know if these rivers in the atmosphere, if they're visible in clouds, and or they just, some of them are invisible to the naked eye. And secondly, how high more or less are these rivers in the atmosphere?
It's a good question. Actually, I'm actually not sure on the height, now that you mention it. I actually don't know if I've looked at that in detail. I don't think they're necessarily visible, though. I just put one image of one up on the screen. It's actually an animation, but unfortunately it doesn't play through this viewer, so you can't see it moving. But the way they're able to see them is with instrumentation that can actually measure the concentration of water moisture in the atmosphere in any one area. So they're not necessarily visible the same way you see things with your eyes. But what they measure is that, like, imagine you took a cup and you had a cup in your hand, and imagine that cup all of a sudden shot up through the entire atmosphere into space. And all of the moisture in the atmosphere, the evaporated water, was condensed to liquid water. How high would that liquid water be in your really, really big cup? And that's what they can measure with these different, that's what you see in this image here, is measuring the millimeters of liquid water contained above any one region in the atmosphere system as a whole. And you can see it ranging from just a few millimeters, a couple millimeters, all the way up to 20, 30, 40, 50, 60, and it looks like it ends at 65 millimeters. There's a large variation. So you can see that this atmospheric river shooting across the Pacific, hitting just north of the northern border of California, looks like it's in the range of 20 to 30, maybe a little bit more, up to 40 in certain parts, millimeters of water in that moisture column of that atmospheric river. So 30, 35 millimeters, where on either side of it, it's more like 5 or 10. So it's this concentrated structure of moisture. And then also Anastasia had sent in a question asking, do we know what creates these currents and shapes of the atmospheric rivers? And unfortunately, I have not done my homework enough on atmospheric rivers to please the crowd here in these questions. But we'll have to look into that more. I'm actually not totally sure. There's a lot out there to read up on it. We just haven't had the time to sit down and read through the different things that have come up. But it's a very fascinating process overall. Because the first thing you ask when you look at it is, why is the water not distributed homogeneously throughout throughout these regions of the atmosphere? Why does it concentrate into these very relatively dense and concentrated structures over these large extended regions? It's a very fascinating question. And it might even go to similar questions of why clouds form at all, what's actually going on with water such that it'll form these structures. You know, some people have asked, you know, why is it when you see a single cloud in a all blue sky and you just see one single cloud sitting there, why does it do it? Why does it work that way? Why does the water moisture so much condense in that one region and bound itself into the one cloud and then leave so much less moisture just right on the outside of the cloud everywhere else? Why doesn't it just, you know, distribute itself relatively homogeneously throughout the atmosphere over a larger area? And those are actually some pretty interesting questions that actually point to the fact that we frankly don't know a whole lot about why water does what it does on the large scale and on the small scale as well.
Can you hear me?
Yep.
Okay. I just wondered because I mean, I'm wondering if Lynn is saying what he's saying about Nawapa now because there's just not going to be that precipitation that we can count on in Alaska and the Yukon and Mackenzie River valleys. And if we can, I mean, would we immediately would we have to gear up a fission power capability to desalinate seawater like immediately, and then you know, that would create the basis for a fusion power desalination capability within the next, say, 10 years, and then we would still need some kind of system to move the water around. I mean, maybe it wouldn't look like Nawapa because you don't have to bring the water down from Alaska at that point, but some kind of integrated canal system, you know, throughout the nation that would allow us to manage the water that we're creating. I mean, I kind of like it because it seems like we're saying we're going to take control, we're going to seize control, and we don't even have to worry about what the hell Canada thinks, but we're just going to control we're going to make water. I mean, obviously we can figure out how to change the weather patterns as well, bring the water down from this area where there's rivers up there, you know, but just a combination of seizing control, using energy flux density to make water. I mean, there's a ton of water in the ocean, obviously. It just has salt in it, so we got to figure out how to get massive amounts of fresh water. I think you touched on it in terms of, you know, if you could desalinate seawater for places like LA, San Diego, San Francisco, that's a huge amount of water that's taken away from the Colorado River system, for example. But anyway, I just wanted to see it's a bunch of different questions, but whatever you want to say about it, I'd be happy to hear.
I think the key thing is the three elements that I listed that I went through in the main part that distinguish the situation now versus the situation when Nawapa was originally designed, which is one, the immediacy of the crisis, two, the physical attrition factor that's been built in to the physical economy due to not building Nawapa, and three, something that was really not known at the time, a greater understanding of the fact that these systems, climate systems, precipitation patterns, they're not just static things we can count on indefinitely into the future. And if mankind's going to have a ability to secure the water we need for a growing global population, we have to go to a higher level conception now. You know, Nawapa and Nawapa style projects on other continental systems absolutely should have been done over the past 50, 60, 70 years. But things have changed since then, and so the solution now, mankind has changed, the climate and the sun systems have changed. We're in a different situation. We have to come to a higher order conception and how to handle and address the entire thing. And we might very well still want to do things like NWAPA, but they have to be thought about and subsumed from this three-dimensional perspective. This idea that we have to think on the scale of the entire, because it is a single system. It's a single global system. You know, there's not much to what might be upsetting to one California congressman. There's no such thing as California water for California. California doesn't have its own water. California gets its water from the entire Pacific system through these atmospheric rivers and these moisture flows. So you're already dealing with a single global system. And even if we had built NWAPA, and even if we had built these other systems, we would still be faced at a point today where we'd want to go to this higher level. If Franklin Roosevelt had lived longer, and he'd secured the type of post-war world, anti-imperial world that he wanted, and even if we had built NWAPA and Transaqua and related continental scale water projects, then we'd still be in a position today, recognizing the weakening of the sun, recognizing the increased evidence that solar and galactic activity actually play a critical part in the changing and evolving and developing conditions we experience on our planet. We'd still be in a condition today we'd want to take this to the higher level. Now we're being forced to take this to a higher level because of the failure to do so, to do this so far, because of the fact that we don't have any studies necessarily indicating one way or the other if what the effect in the north is going to be in the Yukon Basin and the McKenzie Basin and these major river systems up north. We're not totally sure what the effect. There might be studies out there, and we're digging around to see what we can find. I haven't seen anything yet indicating one way or the other what type of variations we can expect with a changing, with a weakening solar cycle and a potential grand minimum on the moisture patterns up there. But the larger point is we can't, overall, mankind can't just subject himself to being subject to the precipitation patterns that exist. We've seen enough now that we know that these things can change rather dramatically, and they can change on the scales potentially of decades. You know, these aren't million years, thousands of years events. We went through some thousands of years variations, and variations over hundreds of years. But even just the records of California and the West show that these systems can change on a much shorter time scale. So it's really the stage of evolution of mankind defined by our level of global economy, defined by our level of knowledge of the sun and our beginning insight into the solar system and the solar system's relation to the galaxy. We've reached a stage in the development of human society, accelerated, where we need to start thinking about the crisis on this level. And our need to think and act on this level is being dramatically forced and accelerated by the existential immediacy of the crisis we're facing right now.
Hello?
Hi.
Hi. Couple questions. One, how do we know that the sun is going into a minimum? What's the background for that? And then the other question is this what Lynn is talking about when he references how Kepler discovered the solar system as a system? And do we have to make a breakthrough on a higher level of harmony going on with the Earth's weather system being connected to the solar system? And is that, though it seems like I'm just reminded by all these different patterns that are kind of coming out in some of the data that you showed, and you're going to look into a lot more of it, that you're going to start looking for different correlations. And what kind of experiments, do you have any in mind of experiments that are going to need to be part of that investigation? Yeah, that's the main question.
Well, on the first one, the sun weakening, there was, I don't have all the studies right off the top of my head. I know one thing, they actually measure, they've done it for a few solar cycles now. We've had decent measurements of what the sun is doing, looking at sunspots, how many sunspots. We can also measure how strong the magnetic field on the sun is. And we can actually measure how strong the magnetic field directly at the sunspots is. So I know one of the things that people are looking at is the fact that the strength of the magnetic field on the sun, and I believe around these sunspots in particular, actually we've seen indicates something about how strong the next solar cycle is going to be. So right now we're at the maximum of solar cycle 24, I believe it was. I think we're at. About 8 years ago, 8 years ago or so, before we entered solar cycle 24, if you look at the official forecasts from NASA of how strong this solar cycle 24 was going to be, they showed that they expected it to be as strong as solar cycle 23. But there were a handful of people who were looking at this phenomenon of the strength of the magnetic field on the sun, and a few other indications. I actually can't quite remember off the top of my head. I can dig up some stuff and maybe we can send out some material on background on some of this. But there were a few other indications. But there were a handful of people that were indicating that the sun is actually weakening, even while we were in solar cycle 23. They were saying solar cycle 24 is going to be much weaker than what most people expect. And they were proven right. And now, looking at the same processes that they were looking at then, we're still seeing a weakening process. We're seeing that the magnetic field is still getting weaker around the sunspots. So based on the evidence used to forecast this weaker solar cycle 24, this same evidence at this point appears to indicate that solar cycle 25, the next one, will also likely be even weaker than the one we're experiencing now. And I believe there's some additional studies about some of the stuff gets somewhat complicated. They believe they can measure what's going on beneath the surface of the sun by looking at the waves on the surface of the sun, and somehow use with some very complicated analysis, looking at how the waves are rippling on the surface of the sun gives them an indication of what might be going on beneath the surface to some degree. And there's certain migrations of structures beneath the surface of the sun, which they've also been able to watch now over the course of at least one, if not a couple, solar cycles. So it's a very new science, but it's something that have been able to look at a little bit now. We've got a couple solar cycles that we've been watching more closely. And so based on these processes we're watching, some people have been able to say what they think might happen in the future with the next solar cycles based on what we've seen happen over the previous few. So it's by no means a fully understood thing at all, but it's not totally baseless. There's been some studies going on now that have at least allowed an initial successful forecast of this solar cycle 24 being weaker. And on the conception of Kepler, absolutely. I mean, absolutely, that's going to be, we're not going to understand the atmospheric system, the weather systems, the climate systems from a kinetic bottom-up perspective. We're going to have to make some real discoveries about the higher order principles governing what the sun is doing, what the relationship between solar activity and the Earth is, and what the relationship between the activity of the solar system and the galaxy is. The only way we're going to figure this stuff out is by taking exactly the method of Kepler and not trying to curve fit or interpret evidence we're receiving about what the sun is doing and what the galaxy is doing from the standpoint of our pre-existing assumptions. We're going to have to look for real principles that actually shatter and break down and contradict the assumptions that are dominating science today. And I would think one area that is already very weak and would be likely to fall would be the conceptions of the second law of thermodynamics and the prevailing ideas associated with that about processes, these astronomical, astrophysical processes when you're dealing with solar systems and galactic systems and related things.
What do we know about the relationship between solar activity and the asteroid problem?
Daniel just asked what we know about the relationship between solar activity and asteroids, dealing with asteroids. And that's a good question. I mean, I haven't seen anything in terms of the variation playing a significant role. It might or might not. I just haven't seen anything on that, on whether it's a grand minimum or a maximum. What is interesting is that one thing that's known, that's discussed, is that all these near-Earth asteroids in the inner solar system, over any geological time scale, they shouldn't be there. They're either going to run into a planet. The asteroid belt's got it's nice, a lot of room in there, right? You got the tetrahedron ratio, so you got a lot of space in there. Plenty of room between Mars and Jupiter to have nice orbits so they can move around. In the inner solar system, you got, they're like butting in on other people's territory. You got Venus here, you got Earth, you got Mars. They're just like driving through someone else's neighborhood, and so they don't last very long on large timescales. Either run into something, or their orbits get perturbed enough that it moves them out to a different orbit, or they just get ejected out of the solar system. So based on that, a few millions of years, tens of millions of years, maybe a couple 100 million years, I don't know what the models show exactly, there shouldn't be any near-Earth asteroids at all. They shouldn't be here because they should all hit something or got tossed out or whatever. So the conclusion is then there must be something that's constantly kind of trickling in more asteroids into the near-Earth asteroid population. There must be some source that's feeding it to keep up, because there's millions of these things in our immediate vicinity. So one thing they look at is actually the role of solar radiation pressure. there's this thing. One thing they look at is what's called the Yarkovsky effect, where they look at the fact that when the sunlight hits an asteroid, it warms up one side of it, and then as the asteroid turns, as it cools off, it re-radiates the infrared radiation in the direction that it's rotating in. And that's a constant process that gives a push just in one direction. So for these relatively smaller objects, these asteroids, which are not very big in terms of the scale of a whole planet, they think that this process can actually take asteroids that are in the main belt and actually slowly change their orbits enough such that they move into one of the Kirkwood gaps, a resonance with Jupiter, where it might send it into the inner solar system, or it might change the orbit enough that it gets a close pass by one of the larger planets and send it into the inner solar system. So that's one relationship between solar activity and the asteroids. The other thing that's been looked at a lot with the asteroids is potential galactic activity and activity of other stars. It's believed that there's this huge population of comets way out in the farthest reach of the solar system. And this actually extends, they believe, a good chunk of the way towards the nearest star. So they think that if our star makes a relatively close pass by another star, it could actually perturb some of these bodies and send them down into the inner solar system. And then another thing, there's actually just a new study published on it just within the last couple months, is that it's not totally clear, but there is some indication that there could be a periodicity in the asteroid impacts, in the very large asteroid impacts. And some people have put this periodicity at about 35 million years, give or take. From what I've read, the statistics isn't totally solid. There's enough to indicate there might be something there. It might actually be a periodicity, or it might just be just kind of an anomaly in the distribution. But if that is there, then that immediately points to there's a new study looking at maybe it's as the solar system bobs above and below the galactic plane. It's about 35 million years between each pass through the midpoint of the plane. And for some reason, I have no idea why, the going idea now is that there's a very thin disk of dark matter in the galactic plane. I don't know what that is or why people believe that, but then there was some people had a new study now about maybe that's why you had this periodicity of the impacts from these large comets and asteroids on the scale in which we pass through the galactic plane. I don't know what to make of this whole dark matter business, but that's a whole other story. But so there is, when you look at the impact scale, there's definitely points you to the solar system motion through the galaxy as a significant factor in that. So question from Mark Fairchild came in. Says there are 2 nuclear power plants in California and 2 in Texas, as far as I could determine. Couldn't we retrofit them with desalination capabilities? And how quickly do you think that could be done? It's another very good question. I'm not totally sure on the time scale. Might want to talk to. We should actually get a better assessment on that. We can talk to some. Do some outreach, talk to some people. I know Marsha Freeman's looked at this a lot, but there's 2 ways of doing desalination. One, using the heat process. Another way, just using the electricity generated. So any place you're generating electricity, you can use the electricity as a way to power or reverse osmosis desalination process. But exactly how long it would take to get that going and up and running, I'm not totally sure, but we should. Other people, I think, might have looked into this in more detail. We should get a clear reading on that. Another thing that comes up in some of this is the time scale of doing it. I know this comes up with nuclear power plant construction, for example. You can get a time scale on what it would take to build 1 or 2 systems. But if you look at the total crisis and the scale of investment needed, and you start talking about tens, dozens, 20s of systems needing to be built, you start to run into a potential construction bottleneck that's not there if you're just talking about building 1 or 2 or a couple things. That's definitely the case with nuclear power plant construction as a whole. But in terms of what it takes to actually build and operate a reverse osmosis or a flash distillation desalination system, we should actually get a better reading on that. It'd be good to have that available.
Ben, just answer the California nuclear power plant question. One of the power plants was shut down last year and permanently. It's being literally auctioned off right now. One more. So only one exists in California, and every kilowatt it produces is used. Right? And California is going to be facing electricity crisis along with a water crisis, both because of the shutdown nuclear power plant and nothing else has been built, plus the hydropower production in California, which is about 13% of California's electricity, will be this year, probably down to 5% or less. So just a little bit on the California there.
Also with that, I was thinking that just in terms of what Lynn is thinking, it's not that we're completely dumping the WAPA idea. Maybe we are, but I was wondering, would it require a similar type of full-on national mobilization in order to get the desalination going? I mean, I think that desalination would be a lot more secure than just a river system or just, replenishing them. And I'm curious if the change in the solar activity does impact our rivers and our water system as it already has, but that you might have things like the McKinsey and the other big rivers in the country not producing as much as they do right now because of the changes in the sun. And so would the desalination be a lot more secure than just even relying on the natural rivers?
Yeah, there's certainly some benefits. I mean, the ocean's not going to go away, hopefully. And if it does, we have much larger problems to deal with than just but the other thing with the desalination is that you have to get it inland, and so it could potentially require a fair amount of pumping requirements. This study that Leona dug up was given by a scientist from Los Alamos. He actually had 40%. So he just did a whole very rough top-down global picture of, say we have 13 billion people in the next, and we need to provide water for them. What would it take to provide that with fusion-powered desalination? And he ended up coming to the conclusion that 40% of the power needed was going to be needed just for pumping the water inland, for pumping the water from the coast where it's, so 60% of the energy goes to desalinating it, but still almost half of the power is then needed, 40% is then needed to move the water inland, potentially up high elevations to where it's needed, to where the populations are. So there's an additional consideration with the desalination, because you have to move the water to where you need it. But overall, again, the water is, if we can get any type of handle on adjusting where that water moves in the atmosphere, and any type of handle on inducing that water to fall where we want it to fall and when we want it to fall, and to not fall where we don't want it to fall, then we're going to a whole higher order capability. And this is actually one of the areas where we actually are using solar power. And solar power actually makes sense. We use solar power in the form of agriculture. It makes sense there. We use the sunlight to grow our crops. The lifting of ocean water, turning it into fresh water and lifting it into the atmosphere, is a huge amount of work that the sun is constantly doing for us. The sun is, I actually forgot the figures off the top of my head now, but the figures are, I believe it's in the thousands of terawatts. I could be off by even a 3 orders of magnitude there, but I believe it's something to that effect of power that the Earth is constantly receiving from sunlight hitting the surface of the Earth. Now, at any one area, any given square meter area, it's at a very low energy flux density. It's a very low power source to try and harness it just for power in that form. But if that's spread out over the entirety of the Pacific Ocean and is evaporating the thin layer of water from the surface of the ocean and then moving that water up into the atmosphere, it actually adds up to a tremendous amount of power that the sun is providing to make all these atmospheric moisture patterns, to put all these atmospheric moisture patterns into existence. So it's a huge potential. It's a huge store of potential that we have to be thinking about acting upon, guiding, and eventually controlling, which will give us a whole top-down grip on the water cycle as a single system as a whole. And in that context, we're absolutely going to want to move with desalination in certain cases. We have existing river diversion and river control systems that we're going to want to ensure that they are able to continue to operate by ensuring they continue to get the water that they need. We're going to want to create new river diversion systems. Potentially we're going to want to build NWAPA in the context of this larger system. But all of this is going to be subsumed by a higher order conception of what can we do with these atmospheric flows, and this 413,000, this 500,000 cubic kilometers, this 20,000 Colorado rivers flowing from the ocean up, directly upward into the atmosphere constantly at all times. What can we do with that? How can we act on that? That's a challenge that mankind is now being faced with these developments we've been discussing here today. Another question here that came in the email. It says, what about giving emergency credit to farmers in parts of the country not affected by the drought to grow crops to offset the decrease in California and the drought-stricken states? I realize we can't just have orange trees spring up instantly into place, but what about things like lettuce and vegetables? And absolutely. Again, I mean, I think the immediate objective to make all of this and any of this happen is to get the British Empire out of control of the United States and out of control of the huge section of the world economy. And with any sane, patriotic government that has any concern about taking care of the needs of the food supply, the physical needs of the population of the United States, we must do these types of measures. Immediately, we can cancel the fracking policy right away. That needs to go to secure water for where we already desperately are running short. We need to absolutely reverse this biofuels insanity, where under a utterly insane policy, we're substituting, instead of growing food for crops for food, we're growing huge amounts of crops for fuel. And the amount of energy that it takes to create ethanol fuel is almost the same amount of energy as you get when you burn it. The profit ratio is tiny. It takes, for every 1 unit of energy you put in to getting ethanol as a liquid fuel, burning that same amount of fuel gives you 1.3 units of energy out. So it's hardly even above break even, just in terms of the net physical energy in, energy out ratio. It's a totally insane policy. Any other power supply that's not an environmental green power supply is on the order of 20, 30, 40, 50, 60-fold increase. You put 1 unit of energy in to acquire the fuel, and you get 30, 60 units of energy out when you burn that fuel. Biofuels is 1 to 1.3. It's complete insanity. It's just part of a genocide policy. So absolutely, we would save any farm that exists that can produce food, has to be supported so it can produce food. And if we had a top-down Franklin Roosevelt-style mobilization, which is what this nation needs for the defense of its population, those types of measures would be absolutely on the table day one of any administration that's going to come in and actually care about saving the U.S. from these conditions.
Hey, Ben, can you hear me?
Yep.
Just really quick, a question on the on what you just said there, that for each unit of energy that you put into the total operation, which leads to the production of these biofuels, this ethanol, that the total per unit of energy that you put in, you get out 1.3 units. That's from the fuel that you can burn?
Yeah, exactly.
Well, so you have that 0.3 margin of energy profit, right? But what is most of the biofuels being used for? It's not for, like, it's being burned in, your car. So only about, what, 20 or 30% of the energy in your gasoline actually gets converted to mechanical energy. So if you wanted to actually burn the fuel that you produced for something like electricity or something like anything else, that margin of profit would be negative. So it's theoretically a margin of profit, but if you actually try to use it for anything and try to recreate the process, it would be negative. You see what I'm saying?
Yeah, absolutely. And that's a very, quite frankly, it would be good to redo some of those studies, because I'm not even totally sure what assumptions these people put into those studies. And I'm sure there's a lot of interest that want to try and make biofuels look as good as possible. And that's pretty hard given the fact that it's so clinically insane. But it'd probably be worth re-looking at those studies to see. But even that is, as you're saying, that's just looking at it in the small, which isn't the whole story by any means. The actual cost, you can't measure the gain to cost just by looking at even that it's a useful illustration to give kind of a rough first order idea of some kind of physical standard to an economic process. But if you're really going to measure any of these things, you have to go to the economy as a whole. The only way you can measure value and determine the value of one action versus another action is by looking at the different effects that has on the ability of the entire economic process to operate. This is what Jason's taking people through with Lynn's economic textbook, and looking at what he calls a thermodynamic model of a physical economic process, and looking at the physical energy of an economic system, all the physical goods, the physical products, the physical production, the maintenance required to maintain an economic process, your C and your V in his terms, and comparing the amount of physical profit you can generate in that same economic cycle, that same economic process. So are you taking actions that allow you to both increase your energy of the system of the economy and also at the same time increase the free energy produced by that economy as a whole? And you really can't take it in any less terms than that. So even these energy policies, that's why the concept of energy density of fuel is so important, because if you're moving from chemical reactions to nuclear reactions, you're literally moving 1,000,000 times in terms of energy density. The energy released per mass, per weight of a chemical fuel is 1,000,000 times less than the energy that can be released per mass, per weight by a nuclear reaction. And in those, you get higher energy per mass from fusion reactions than fission reactions. So right there you have the potential for producing a much higher rate of power production relative to your economic process when you move towards these nuclear reactions. And assuming you had, assuming you had a roughly similar amount of labor force required to maintain and fuel a nuclear plant versus a coal plant, which wouldn't be the case, but just even take that as a rough example. So say your physical cost to society to operate those systems is similar. With the potential of a higher energy density fuel, you have your same physical cost. Your energy provided to society is a function of the physical input to sustain and maintain that production leaps orders of magnitude. And if you're not constantly increasing that ratio, that power, you're going to have a net loss on the economy as a whole. So biofuels, if you just measure it in the small, might look like it has a small gain. I mean, it's a pathetically insane small gain that no one would ever do in their right mind unless it was being pushed as a top-down policy. But even that, looked in the context of the whole economic system, is a dramatic net loss, net physical loss to society as a whole.
We got a question here.
Oh, it's just a comment.
Or comment. Go ahead.
Yeah, also, Ben, on the ethanol, I think we've read that it takes about 1,000 gallons of water to produce 1 gallon of ethanol. So it kills us on the waterfront also. And on the nuclear power plants in Texas, they only provide 6% of the power required. And one of the plants is in the middle of the state. So we would have to build new plants to do the desalination.
Did you hear that comment from Joel?
Yeah, absolutely. That's
Okay.
very. I mean, this green stuff is just so utterly insane. It would just never have any support at all if it wasn't being pushed as a top-down policy, including all the subsidies and everything. I hadn't heard that specific figure on the 1,000 gallons of water to 1 gallon ethanol, but that makes a lot of sense, and that's probably something we should actually get a handle on and get a clear analysis of and maybe put out, because that's just obviously completely suicidal and insane to have this still being pushed as a national policy.
Yeah, Ben?
Yeah.
I was going to ask first about the rivers, the atmospheric rivers, and you said they don't stay around very long. And I was originally wanted to ask whether there was some way anybody had thought about the idea of cloud seeding, but that of course is high up in the stratosphere. I don't know whether this technology that Mexico is working on has been done by anybody else, whether that might have some impact on something like that at that high altitude. I don't know. Do you think that's possible?
Yeah, I think so. I haven't looked a whole lot into the details of the cloud seeding work, but that's something that's pretty actively done across the United States and across the world. As far as I understand it, you're basically, if you have, it's dependent upon having a certain amount of moisture in the atmosphere above where you want it already. And if it's there, then you can kind of induce it to condense and fall if it's relatively close. I don't know exactly how close it has to be in terms of water density or how moist it has to be to get it to actually fall down as rain. But that is something that they have national cloud seeding weather modification organizations that meet and talk and collaborate. It's a pretty active area. So it certainly can be included as part of the whole top-down perspective. But the additional challenge that we have to now begin to look at is how do we, that depends upon the moisture being above the region where you want it. So then if that moisture is not there, how do we bring it there? How do we begin to move these flows of moisture around different regions up in the sky? And it doesn't necessarily have to be an atmospheric river. Just even, I mean, these rivers are kind of fascinating structures to study and investigate and look at the potentials available up there. But to get the water that we need, it doesn't even necessarily require something as intense and structured as one of these atmospheric rivers. Even just your regular evaporation moisture content that's constantly rising up above the oceans could potentially be something that we could act upon and entice to move inland and provide the moisture flows that we need. I have a question from Mexico. Could you address the idea of energy flux density from the standpoint of the temperature of the process? What is hidden there with the temperature? Yeah, that's an interesting, a very good question. Because at a certain point, you really have to look directly at the question of the quantity or the quality of the energy above the quantity. And there's certain, immediately certain things that become very good case studies to look at. One is certain chemical processes can occur only at certain certain levels of temperature. So that's something that's, for example, being studied with some of these fourth generation nuclear reactors, is the fact that if you have a high temperature or a very high temperature reactor, I think some of these are looking at operating at 900 degrees Celsius, I think is one of the ranges they're looking at that would open up some of these things. One big area that's being investigated is getting hydrogen from water by a process called thermal cracking, where you can, if you have a certain high enough temperature, and I forget exactly what the threshold is, all of a sudden you open up an ability for a chemical reaction to liberate hydrogen from water, and now you have a much easier access to a hydrogen production capability. And there's a whole array of these types of processes. I think Leona covered some of this pretty well when she was looking back through the old Oak Ridge National Labs Nuplex nuclear agro-industrial complexes reports that were being done back in the 50s and the 60s, and they were looking at how to use nuclear power as part of an integrated production process, and be able to use the excess process heat, use the high temperature heat generated by certain nuclear reactors directly in certain primary energy applications for certain chemical processes, potentially certain industrial processes, fertilizer production, other types of things. And I think some of that was included in the Nuclear NWAPA 21 special report. So that's absolutely, you open up certain new avenues of action when you look at the quality of the energy versus the quantity. And temperature is often associated with that type of change. The other thing on this, energy, when you say energy, if you have energy in the form of, say, a fast neutron coming out of a nuclear reaction, that has the potential to transmutate and change one element for another into another. If you had that same amount of energy in any other form, you couldn't do that process. So your ability to do work, to make productive, valuable changes in society, in an economic process, or in the universe generally, is just not measured by energy. Energy can't measure work. You can measure work by qualities of energy, and the application of certain qualities of energy that are tuned to the types of processes you're trying to act upon. And this you can measure with the energy flux density, as Mr. LaRouche has obviously developed. So I think that's obviously a big thing that we run into a lot, is we live in a post-industrial society and people are very brainwashed with this conception of energy and energy accounting. including as it applies to second law of thermodynamics and these scientific considerations. Whereas reality is not measured by energy per se. You have to go to a higher order concept of the energy flux density of a system and your ability to do different higher forms of work as a function of the quality of the energy you're employing and how you're employing it. Another example is this fusion torch or plasma processing studies that we've looked at, where people were looking at using the plasma of a fusion reaction or creating a very, very hot, high-temperature plasma, and then putting material into that plasma and using those incredibly high temperatures to break that material down into its constituent elements. So you break all the chemical bonds and you break it down just to its basic chemical elements, and then you can control and modulate where these elements go and sift out these elements with different magnetic fields and related processes. And this can completely revolutionize the materials production. So EIR and the Fusion Energy Foundation have done some very fun, interesting, and useful studies on these types of considerations of the relationship between energy flux density and temperature and production, actual work accomplished. And you get funny phenomena like you can actually measure the change in how productive your energy is. So when you move to a higher energy flux density, your energy actually becomes more productive. This is very clear in a case study of iron production throughout the history of the United States. The amount of iron that could be produced per unit of energy increased many, many fold over the course of technological development, technological improvements, and most importantly, higher energy flux density production processes. So your actual kilowatt hour is becoming more and more productive. So energy doesn't measure work, it doesn't measure production. Any more questions or thoughts, comments? I think we've lost a few people on the Hangout. We're still joined by George Washington, so that's encouraging.
That's Chris.
Yeah.
Thank you very much.
Well, this is an article I was mentioning on the ionization systems.
Isn't that online?
Yep, it's available. It's in the this edition of 21st Century. My screen's flipped. Huh? You can also get it on in the EIR site. And it's a useful introduction to some of what I went through today, and about three case studies of places where they're actually doing this or they have done this with some degree of success. So it's not the end; it's the beginning of a certain direction of work that we need to challenge ourselves with getting into in terms of the electrical ionization side of affecting and controlling these moisture patterns in these weather systems.
Thank you.
Thanks. Okay.
Thanks, Ben.
We'll talk to you guys later.
Yep. Good night.
Night.